All right, today we're going to get into learning other ways on identifying direction. And when we're looking at identifying direction, we have talked about the standard form of angle before, and the standard form is where we have something where it goes from the positive x-axis to the terminal ray, and that's going to be my direction of that angle, and that's the standard form. That was chapter 1, and we've gone away from this, but we will be coming back to it in chapter 3. However, since then, what we've seen is bearing. And so I now have an angle where it's going to be off the north or the south end. And so when I label this, it's going to be north, theta, west. The third way that we're going to see today how to label an angle is going to be from the north line. And the way they say it is from due north. And once from due north, what that means is you're just focusing in on the north end of a line and going clockwise from the north end of a line. So that means that we're going to be looking at drawing something like this, where that would be my theta from due north, like 200 degrees from the north. And so that's just one more way of drawing in an angle that they're going to use in story problems. Now, important to note that in this book, it doesn't say exactly how to label your answer if you're finding an angle. Do you want it in degrees? Well, degrees it'll say, but do you want it in terms of bearing or from due north? And the way that you'll know which way to leave it is the information on the other parts in the story problem. So if it's talking about from due north in the directions, you know your answer is going to be from due north. If it's talking about bearing in the story problem, you know your answer is going to be in terms of bearing. So follow the guidance in the story problem, and that will give you an idea of how to label a particular angle. We're going to go to vectors, and the first vocabulary list here is a long list that is basically coming down to a type of story problem where you have a boat or a ship. And the boat or the ship is going to go into one direction, and then it's going to be affected by a vector like wind or current. And then because of that impact, it's going to have a resultant vector, which is, in my words, going to be a resultant vector. So you have an initial, you have an impact, and then you have a resultant. And that's what all of these terms are about. Vector talks about, that's different than array. A vector has both magnitude and direction. Magnitude is length. Direction is like bearing. For example, if you were going at 5 miles per hour due north, that is a vector because it has length and it has direction. So whenever you're dealing with vectors, you have both of those components. And then it just, scalar is just a number. Magnitude is the length of a vector. True course, ground speed, airspeed, and heading all have to do with this drawing that we're going to do from page 102. And so let's do this drawing and make sure that that's making sense what the words are. So let's see. So what I want to do is make this drawing from 102 and show what how those words are related to the drawing. First thing I want to do is draw a north-south line, and then let's say, for example, we're in a plane. The plane is going to have a heading, and the heading is going to be the initial heading, and that could be in terms of a bearing, or it could be from the north. But then what happens is, after you have that heading where you set everything up, the wind is going to blow it off course. And so then you're going to have an impact, and it's going to be a different north-south line. And that can be something like wind speed. At the end, you're going to have the result, and that's going to be ground speed. What's the speed in relationship to the ground, like the actual speed after the impact? And also with this, you're going to have an angle, and that angle, which is the finishing angle, is going to be the true course. So true course is actually the true direction of the plane. That's the finishing angle after the impact. I like to think about this in terms of initial. You have an initial direction or initial ray. That's going to be now affected by an impact ray, and that's going to create a resultant vector, I should say. The problems we're dealing with, we'll say what's the true course of the plane or the boat. That's going to be this green one. What's going to be the ground speed? That's going to be the green one. Often is the case, you're going to want to hone in on the north-south line as well as the finishing vector, or else it's going to, because it's going to get messy with these drawings. Make your drawings really big. You really want to see what's going on in them. Okay? Do not have small drawings in these. There's plenty going on. Let's go back and talk about a couple more ideas. These ideas are pretty simplistic in terms of what a vector is and how to label a vector. The notation of a vector is where you have like a bold V or a V with an arrow above it. That's how you know it's a vector. The magnitude of a vector, or the length of a vector, is denoted as the V, but along with the V is a parent absolute value sign. Absolute value, we know, is always a positive distance, and so it would make sense that the absolute value, which is positive, would go with the length or the magnitude. Then we have vectors, and vectors are like rays, but they have direction as well. So for example, if you looked at this first particular vector, that vector is going to have a length, but it's also going to have a direction south. Vectors can be equal. Vector 1 and vector 2 are equal because they have the same length and the same direction, like this pen. You can take this pen and move it around anywhere. They're all going to be equal vectors. Same length, same direction. But if you switch the head and tail around, then all of a sudden this vector is not equal to this one. They're actually opposites. One is negative, the other one, which is right here. I'm not going to spend a lot of time on vectors and adding and subtracting. I did that at the beginning and found that that lesson was taken away from the story problems. The main thing on vectors that you should know is there is both length and direction, and it's different than a ramp. We're going to use vectors in ship problems, in airplane problems, and even in shooting problems with cannonballs, where they're going to just represent both direction and length. I want to go through some examples, and it's important that when you do problems to draw them in your notebook. Do not say to yourself, the problem is drawn in the textbook so I don't have to draw it. You want to redraw the problem. You want to draw it. So on your paper, you can actually put information in, and as you go along, plus when you draw it, you're more familiar with the problem. Make sure you're drawing everything as you go along. First thing I want to do is, at the example number 1, it talks about a boat crossing a river. And again, when you draw these things, we're going to want to draw them one step at a time, so I'm sure that I'm doing this correctly. I don't want to read the whole thing and then draw it. I just want to do it one step at a time. A boat is crossing a river that runs due north. That means you have one big river where the direction is going north in the direction, okay, so the river goes north. That means the current is running north. The boat is pointed due east and is moving through the water at 12 miles per hour. 12 miles an hour. It's not the actual speed of the boat, it's the initial speed before the current is weighed in. Then it says the current, which goes with the river, is moving at 5.1 miles per hour. 5.1 miles per hour is where you have the impact. I have an initial, I have an impact, and because of those two things, I have a resultant. The red is where I'm focusing on and where I need the information. The question here is find the true course, but what we really want to do is find the true course and the actual speed of the boat. How do you do that? Well, the first thing that I want to do is to find the true course. I have to think angle. And it doesn't give my angles and bearings because they're basically east and north. So I'm going to just pretend that it's in bearing because I don't know which way to label it on this particular drawing. That means for bearing, I want to drop a north-south line. When I drop that, I'm going to want to draw in what exactly I want to find, which is my theta. That's bearing from north. So it'd be north, angle, and then east. And at this point, I know that this is going to be my theta as well because those are alternate interior angles. And now I can just work within that triangle. That's not too bad. I know opposite over adjacent. Tangent theta equals 12 over 5.1. The work is fairly easy after you set the drawing up, but the effort should be all in the drawing. this becomes 67 degrees approximately. And so if I were to label this in terms of bearing, it's going to be north, 67 degrees. For your homework, I'd like you to go to the nearest hundredths, always round at the end, and that's going to be east. So that's my true course. Remember, always from the north-south to the resultant. The ground speed, or the actual speed, is going to be what your x is. On this problem, it's just Pythagorean theorem. You know it's a right angle because it's north and east. Those are going to hit at 90 degrees. And so it's just going to be x squared equals 5.1 squared plus 12 squared. And when you do that, if you're dealing only in terms of whole numbers, you know it's going to be approximately 13 because of the 5, 12, 13. But again, I want you to go to the nearest hundredths. I'm just doing this for time's sake. And therefore, this is going to be the ground speed. So you have two answers, which make up the vector, the resultant vector v. You're going to have a true course, which is the bearing, and you're going to have the length or the magnitude, which is the ground speed at 13,000. I want to set up the next problem, and this is going to get into the words that we talked about at the beginning. Right after I get done with this. We talked about this at the beginning of the class, but just to reinforce it, we're looking at bearing versus heading. Book is going to use these things interchangeably at this point. You have to just be able to do both. And so the bearing, as we know, goes either out the north or the south end and is south 32 degrees east on that drawing. But when I go to heading, heading has to be off of the north line. So when I draw this, this is going to be 148 from due north, and 148 degrees from due north is the same thing as my bearing of south 32 degrees east. They're the exact same angle, the same direction, except we can label them differently. Take a look at example number 2. And I want to be real careful here on these drawings. I'm going to use that drawing that I'm actually looking at on page 102. And I want to be careful the way that I label these things. So again, one piece at a time when I draw these. And if you take your time and don't try doing everything at once, I think you're going to be fine. A plane is flying at 170 miles per hour with a heading of 52.5 degrees. The heading is the actual starting direction of the plane. Because it doesn't give it in bearing, I'm thinking from due north. Therefore, first starting, I'm going to draw a north-south line, 52.5 degrees, and it's going to be 170 miles per hour. That's my initial. Then it says the wind currents are a constant 35 miles per hour at 142.5 from due north. I need to draw I want to drop another north-south line because it's an impact. I'm starting over. 142.5 degrees. From due north at 35 miles per hour. Now that was way too long, so I'm just going to adjust that at 35 miles per hour. The question: find the ground speed and the true course of the plane. Find the resultant vector. I need to draw that in. I want to find out what x is, and I want to find out what this angle is right there, which is my theta. Keep in mind your initial north-south line and your finishing vector. That's the angle that you want to concentrate on and not get distracted by the other information. All right, first of all, looking at the ground speed, x. The ground speed is where you're looking at the triangle trying to solve for x. How do you do that? Well, the way you do that is you have to know that it's actually a right triangle to use the Pythagorean theorem. I'm not shown that it's a right triangle at this point. I need to understand that it is a right triangle so then I can use SOHCAHTOA and the Pythagorean theorem. How do I know that this angle right here is 90 degrees? The answer is you have to think about alternate interior angles. So I know that that angle right there is going to be 52.5 degrees because it's the same angle here as it is here. Alternate interiors, first of all. Second, I need to understand what this angle is right in here because they're supplementary to 142.5. They lie on the same line. So if I know that this plus that angle equals 180, then that's got to be 37.5 degrees. Now I know this is 52.5, this is 37.5, which means if I add those together, that's going to give me 90 degrees. So now I know that this is a 90-degree angle. I've confirmed that that's 90 degrees. Now I can go ahead and get my information. First thing I want to do is solve for x. That's going to be the ground speed. All right, so this means x squared, which is hypotenuse, equals 170 squared plus 35 squared. And x is going to be approximately 174 miles per hour. You would go to the nearest hundredths. I'm just doing this on convenience sake at the moment. Which is the ground speed, and I'm done with that. Now I want to do the true course. True course is the angle at which the resultant is affected. And so what you really want to know is what is the actual direction of the plane. What's the actual direction? I want to know what is my theta off the north end. So what I really need to do is calculate this alpha to get my theta. How do I determine what alpha is? That's the tangent, because you're talking about opposite over adjacent. Sorry. Tangent theta, tangent alpha is equal to the opposite over the adjacent. So that's going to be 170. Tangent inverse and you're going to see that's 11.6. Now, I'm not going to just write that as my answer. I'm not done. Some students will stop at that point and think they're done. Go back to the drawing and find out, is that really what I want? What I want is my theta, not my alpha. In order to get my theta, I need to add the 52.5 to it to give me my theta. So my theta really is going to be approximately 64.1. And again, I'm looking back in the directions because it was a long time ago. How is this labeled? Heading or bearing? Look, or from due north or bearing? And what it's saying is it's going from due north. So that means I want this answer to be from due north. Now I get that is what it is, and I can stop at this point. From due north. Two answers, ground speed and your true course. Most of the effort would be on the drawing. We want to make sure the drawing is correct before I move on. In this homework, make sure that you're spending time on your drawings. Double check them before you get moving. And then we should be able to hopefully be talking the same language and sound correctly. Remember, test on Thursday and